Alright, so this is the second video about kinematics. We're going to, this is going to be more like a mini unit. We're just going to be talking about projectile motion specifically. And yeah, let's just get into it. So we have a building. I said already, if I decided to drop a ball, I could figure out how far it traveled when I dropped the ball. Or how far it traveled given the time if I dropped the ball. This time, I'm not going to drop the ball. I'm going to throw it horizontally. Not vertically, so vertical, there's no vertical velocity. I don't give it, it doesn't have any speed in the vertical direction when it starts. It only has horizontal velocity. So I'm going to call this in the x direction. So I'm going to say this is Vx, and Vx is 0. Or sorry, Vx exists, it's going to be constant throughout the entire journey. Now, why is it going to be constant? Well, if you remember, acceleration is our change in velocity over time. So if acceleration is 0, that means our change in velocity is going to be 0. When we throw a ball, let's ignore air resistance for now. When we throw a ball, there's no forces, there's nothing pushing on the ball, there's no acceleration that's going to act onto the ball. So the ball is just going to continue in the vertical direction, or in the horizontal direction, at the same velocity for the entire duration until it hits the ground. Alright, what about the vertical component? Well, at first, the vertical component, which I'm going to call Vy, it starts off as 0. And the reason it's 0 is because when we dropped it, or when we threw it, we only gave it a horizontal push. We didn't apply any speed to it vertically. But it does change over time, because we have gravity acting on it. So our g is going to be the thing that's accelerating our velocity. Right? And again, this is a kinematic situation. In kinematics, I don't have to say A average because my A is constant, so it's going to be the same acceleration in the entire trip when the ball that the ball takes. So let's say we wanted to find how far this ball traveled. Well, how do we do that? All right, so let's say that we know our building is 20 meters high. Maybe we did the same test as we did before, and we found it was 20 meters high. Well, how fast, there's one question I want to answer first. How fast is it going in the vertical direction after it falls to the ground? What is the information that we're given? Well, we know our initial velocity in the y direction. We're only finding y direction, right? So we're only going to consider things in the y axis. So our initial velocity in the y direction is 0, like I said before. What else do we know? We know our acceleration is equal to, again, I'm just going to assume g is 10 meters per second squared, even though it's 9.801. It's a lot easier to do calculations this way. And then, we also know that the distance the ball is going to travel when it hits the ground, our delta x, or our displacement, is equal to 20 meters. Now, if you remember our time not found equation, we know that v, the final velocity, squared, is equal to the initial velocity squared plus 2a delta x. So, what we can do to find our final y velocity is we can actually just plug in values. So, yeah, let's just do that. Let's just plug in all the values that we know. So here we can plug in 0. So this turns into 0 meters squared per second squared plus 2 times 10 times 20. So that's like 400. And what are the units? The units are still meters squared over second squared, meters per second squared times meters. So that means our VFY squared is equal to this. Well, that means if we take the square root of both sides, we get our VFY, our final velocity in the y direction, is equal to 20 meters per second. Because the square root of meter squared over second squared is just meters per second. So there we go. We found our final velocity. That is awesome. Now can we find the time that the ball took to travel to the ground? Yeah, of course we can find the time, because we know that A is equal to delta V over T. So that means T is equal to delta V over A. And delta V is equal to Vf minus Vi. I'm going to put a y here to remind us that we are working in the y direction, divided by A. Do we know these values? Yeah, we just calculated the values right here. Yeah, so I'm going to erase the work we did, and let's just plug in our numbers. So we have VFY is 20, so T is equal to 20 meters per second minus 0 meters per second divided by our acceleration of 10 meters per second squared, and we get that this is equal to 20 meters per second over 10 meters per second squared, which I get is 2 seconds. If you check the units, this division works out, because the units are meters per second divided by meters per second squared, so that's multiplied by second squared over meters. You'll notice it cancels out, so we are left with seconds. Cool. So now we know the time that's traveled before the ball hits the ground. Alright, the final thing we want to do is we want to find the vertical displacement. So let's write down all the information we know right now. So we know that our final velocity in the y direction is equal to 20 meters per second. This is a coincidence, by the way. It's not always going to match up as the height. And then our time traveled is equal to 2 seconds. Well, if I want to find our delta x in the our change in position in the y direction, or in the x direction, I'm going to use another equation. But first things first, usually when we work with two variables, it gets confusing if we use delta x as distance, so I'm going to change this to delta s, so it's easier to understand. Delta s is my change in distance, so or change in position. Alright, so we know the equation Vx average is equal to delta s in the x direction divided by t. Okay, well, we know, I said before, this velocity is constant, so Vx is constant. Why? Because ax, there's no acceleration in the y, or in the x direction. So it is 0. So I can just say Vx here. Alright. So, delta Sx over t. So, that means t is equal to delta Sx over Vx. Okay? Oh no, we want to solve for our change in displacement, sorry. So that means our displacement, our change in position, is equal to t multiplied by Vx, our initial vertical velocity. So that means that this is equal to 2 seconds times our initial velocity. And we've solved it actually, because no matter how you rearrange it, you can't figure out what this initial velocity is. So the problem is always going to give you this initial velocity. So let's say the problem gave us that this initial velocity is, what's a fun number? Let's say we're super fast and we can throw it at 100 meters per second. Alright, so what would our change in distance be in the x direction? Well, that's just 100 meters per second times 2 seconds, and we get 200 meters. So that's a basic way we would solve these kinds of problems, and this is how you would want to approach it. You would say, what variables do I have? What am I trying to find? And then you want to say what equation uses all the variables that I know and the variable I want to find. The time not known equation is a wonderful equation that is usually used in these kinds of problems if they don't give you the time that's fallen. If they only give you a distance, you know the acceleration, and you know some velocities. Alright, so the next thing I'm going to talk about is projectile motion. So let's say instead I actually what I actually do is I have a cannon on the ground. Here's the ground, here's my cannon. And I'm going to fire a ball. And I'm going to fire at some initial velocity v. Well, we can break down this velocity into two different components. It has a component in the x direction, so I'm going to call this Vx. Oh shoot. There we go. This is a dotted line. Alright, this is Vx, and it has a vertical component, which I'm going to call Vy. If you notice, Vx plus Vy, so this length this way plus this length this way is going to equal my initial vector. So if I draw it up here, this is Vx, and this is Vy. and the x and y axes are perpendicular to each other, so this forms a right triangle. That's something good to keep in mind. Alright, so in order to keep in mind that right triangle thing, I'm going to draw a right sign here. Alright, I'll draw this a little higher. Let's draw it right here where it belongs. And that is our Vx. Right. So, what if the angle that we fire at is theta degrees? Theta is just another variable, it's a Greek letter, so that's kind of cool. Yeah. So my question is, 1, what's the highest it can go? And 2, what is the furthest it can go? Well, to answer how high it can go, what we can do is we can use the time not known equation actually. So first, here's a concept I want you to see. If I have a marker, right, and I throw it up, what is its velocity when it hits the peak, when it's at its highest point? It's going to actually be 0. It goes up, right? It starts up with vertical velocity, or velocity that's going upwards, it slows down, then it stops moving, and then it comes back down, and the velocity goes down this way. So the change in velocity is like this, 0, and then it goes down like this. It goes up, 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 0, and down, down, down. So if I draw a ball, it starts off, if I throw it up, it starts off going really, really fast. But gravity is pulling it down, so I'm losing some velocity. So at the top, the velocity is 0. But then, as it comes down, it starts at 0, and then it goes down, and then it goes faster, and then it goes faster, and then it's going to come down with the same velocity I threw it up at. That's a fun thing that you can try to prove. Show that the velocity that I start at is going to be the same as the velocity that it ends at, given that gravity is constant, and we throw it straight up and down at the same height, to the same height. Alright, so let's get back to this problem. So, our initial velocity in the y direction is Vy. If we remember our trigonometry, we know that sine theta is equal to opposite, so that's Vy, over adjacent, so that's V. If I do some rearranging, I get that this means that V times sine theta is equal to Vy. Alright, so instead of writing Vy, I'm going to write V sine theta every time I say Vy, because these two are equal. So I'm going to write that right down here so we remember it. Vy is equal to V sine theta. Similarly, the cosine of theta is this over that, is Vx over V. So we can rearrange and we can get Vx is equal to V cosine theta. Alright, so these are two things to keep in mind. Alright, so now let's apply our time not known equation. What we know is that our final velocity squared is equal to our initial velocity squared. Oh, I don't need an arrow because these are my... Okay, it's good to have arrows, but I won't put them there because I'm really tired right now. Plus 2a delta x. Alright, so in this case, the only acceleration that's being applied in the y direction is going to be gravity. So I'm going to change this into g. And then we have delta x. So what we want to find, or delta s, right? Because change in distance, and we don't want to confuse ourselves that we're going the x direction when we're actually looking at things in the y direction. Alright, there we go. What is our initial velocity? Well, our initial velocity is just Vy. When it's shot out of the cannon, it has a vertical component of Vy. So, right? So what I'm going to do is I'm going to plug in for this. Actually, I'll just keep it there. And I'm going to say for this, I'm going to plug in V sine theta, or Vy, right, squared. What is our initial, or our final velocity when it hits its highest point? I said it's 0 because it stops momentarily. So I'm going to say this is 0 meters per second. So let's rearrange real quick. We have 0 on this side, we have V squared sine theta squared on this side, right? So I say we can rearrange so we get delta S times G, or we can just plug in everything right now, and then we'll start rearranging to solve for delta S. So we get 0 meters squared over seconds squared is equal to V squared sine squared theta, because V sine theta squared, right, plus 2g delta x. I want to solve for delta x, so I say delta x is equal to negative 2g delta x is equal to, I'm going to move this line to this side, v squared sine squared theta. And then I'm going to divide both sides by delta g, or 2g. So I get delta x is equal to negative v squared sine squared theta over 2g. And now if you remember, delta x is equal to, oh shoot, I keep using delta x. Hard habit to lose. Okay, so our delta s in the y direction is equal to our s final in the y direction minus our s final, our s initial in the y direction. Right? Is equal to negative v squared sine squared theta over 2g. Alright, so now that we have this, what we want to do is we want to solve for our final height. So we're going to assume our initial height is 0, because it is 0, right? Our initial height is 0. We start at the ground, and we want to find how high it went. So that means that I can just say this is 0, and what I get is I get that s, fy, our final position in the y direction, is equal to negative v squared sine squared theta over 2g. You might be asking, isn't this giving me a negative number when it's clearly going higher than 0? That is a good point, but that's because g is negative. G, we are working with g as being equal to negative 10 meters per second squared. Right? So, what some physicists do is they just consider, they don't consider g as negative, but instead they consider g as just 10 meters per second. Instead, what we would be working, if g is equal to 10 meters per second squared, then we actually have this. We have 2 times negative g. So in the end, this is equal to v squared sine squared theta over 2g. Now that makes a lot more sense because we have all positive numbers. This is a square on the top, that's positive, 2 is positive, and our g is positive. Perfect. Our height is positive. This is our equation that's going to define height. Alright, so now on to the second thing. The second thing we have to know is that, here's a big disclaimer, right? We're using g is equal to 10 meters per second squared. If we were using g as negative 10, then this would be this equation, or without the negative g. Alright. Now let's say we want to find the distance it traveled. Alright, so how can we do that? Alright, so I'm going to write in the top right corner the first equation that we just learned. The first equation is s, the maximum height that it can reach in the y direction is equal to v squared sine squared theta divided by 2g. And here's our disclaimer. Alright, so the next thing we want to find is we want to find how far did it travel before we reached the highest point in y. So this is actually going to be us finding the maximum distance traveled in x over 2, because it's first going to travel all the way up, and then it's going to travel all the way down. And x distance is going to be the same throughout the entire journey, because it's going to take half of the time to travel all the way up here, and half the time to travel all the way down here. Alright, so let's solve for this. How much time has passed for the ball to travel from here to here? Well, we know that delta s in the y direction is equal to this distance. So v squared sine squared theta over 2g. What we also know is that our average velocity is going to be, in the y direction, is going to be the sum of its final, right, vfy plus viy over 2. Its initial velocity is this, so that's v sine theta. But what is its final velocity? Well, that was 0. So in fact, this is going to look like this. Alright, so that is kind of cool. But the nail in the coffin is that we know that vy at bar y is equal to delta sy over t. So that means that t is equal to delta sy over v bar y. Right? So to find the time it took to go from here to here, all we have to do is divide this by this. So let's do that. This top part divided by the bottom, or the numerators divided by each other, is simply v sine theta. The denominators divided by each other turns into just g. So that is the time that has elapsed. That is something awesome to know. That's the time that elapsed to get halfway. Alright, so the next thing we're going to do is we know that the vertical velocity is constant, right? The horizontal velocity is constant because there's no forces acting on it, there's no accelerations, like we said in that ball problem. So this is actually just going to be equal for t, our time to get to the halfway point, I'll denote h for halfway, multiplied by our vx, which is v cosine theta. Alright, so now if I plug things in, what do I get? What are the things that I get? Alright, so I get that this is equal to this. So I multiply v sine theta times v cosine theta, so I get v squared sine theta cosine theta divided by g. Alright, next thing to know is we can use the sine double angle formula, and we can simplify this as v squared sine 2 theta over 2g. Because sine 2 theta by the sine half angle or sine double angle formula is equal to 2 sine theta cosine theta. I'm going to just write c and s for simplicity's sake. Is equal to 2 sine theta cosine theta, right? So we know that sine theta over 2 theta over 2 is sine theta over times cosine theta. We have sine theta cosine theta here, and here we have sine theta over 2, or 2 theta over 2. So that's how we did that. So now let's say we wanted to find s max x. Well, we multiply both sides by 2, and what do we get? We get that s max in the x direction is equal to v squared sine of 2 theta divided by g. Alright. Those are the two equations I'm going to teach today. Those are two good equations to memorize if we're on the AP test. And there is one more equation that's kind of cool to memorize. And that equation is this. We're going to be considering an entirely different scenario. Alright, so this is for our cannon scenario where we start at the same height that we end at. Alright, so we start at the same height that we end at. So I'm going to draw the path that the ball takes like this. Alright, and we assumed for all of the things we're doing, we know that v in the x direction is equal to v, or initially in the x direction is v cosine theta, and we know v I y is v sine theta. And we assume that g is 10 meters per second squared is positive. We don't have to assume it's 10 meters per second squared, we just have to say g is positive. Alright, next thing we're going to do is, what if we started our cannon on a building and we shot it up at an angle? What would be the final velocity? Or what would be the final distance? Well, interesting enough, this same formula applies to this situation as well. You can think through why it would apply. This applies to this situation for the maximum height it goes to. But this is going to be the distance from here, from the top of the building to the top of the arc. What if we want to find the distance that the ball traveled when it hit the bottom? This is a formula that you can put onto your formula sheets for the AP test, and it goes s max s x is equal to v squared over 2g multiplied by 1 plus the square root of 1 plus, I have a cheat sheet here because this is a hard formula to memorize, 2g y naught divided by v squared sine squared theta, v squared sine squared theta, right? And then all of it is multiplied by sine of 2 theta, right? Now you can think where this y naught is its initial starting height. So this is y naught. Now let's think how this relates to this, because that's the thing I want to do. Well, if our y0 is 0, if we started at the ground, what happens to this? Well, we get that this thing is 0, because our y0 is 0, so this entire term is 0, so inside the square root we only have 1. So this parentheses, we have 1 plus 1, so that's 2. So we have v squared times 2 over 2g times sine of 2 theta. Right, so the 2's cancel out, and we get the same equation as before. So there is your last equation, and happy studying. This was my mini video, and I hope you enjoyed. Yay!